However, if the Big Bang is correct, then our universe is expanding, and if expanding is cooling off, so today is here, and so as we wait, the universe is further expanding and is cooling off further. That means if you go back in time, the universe is smaller and hotter. Okay? And then in fact, you can calculate that when it's very hot, what will happen? All the nucleus can be formed, atoms can be formed, and so nucleosynthesis nuclei form at a very early stage, when the universe is very hot. But that also means that today, the universe will still have some top temperature, and so in this Big Bang theory, there's one simple prediction, okay? And that prediction is that today, the universe still have a little temperature, and we call that temperature 3 degrees Kelvin. Okay? Now 3 degrees Kelvin is roughly minus 270 degrees Celsius, very, very cold. But still, 0 degree Kelvin will be the absolute zero temperature. Okay? So 3 degrees actually means that our universe is living in a thermal bath of a small temperature, okay? Not above absolute zero. So, if that's the case, we can say, what do we mean by 3 degrees? Well, that means we live in a thermal bath with a lot of photons, radiation, that some of the radiation are actually in a microwave range. Okay? Microwave, you have a microwave at home. The size of a microwave, that's the length of the microwave. A cell phone uses microwave. Okay? A lot of crucial communications now involve microwave. And the reason in 1964 this becomes all of a sudden Big Bang theory become accepted is mostly because they detected this microwave. Okay? They detected by accident. They work for Bell Lab, which is a communication company, and in those days, TV used antennas, and what antenna we receive from the sky, and what we receive from the sky, antenna, if you don't have a good signal, the screen is like this, okay, which nowadays you have cable, you don't have that. But in those days, you have sort of very badly receiving, and you're taking all the noise in the sky, and 1% of this noise is essentially the cosmic microwave background due to these 3 degrees Kelvin. So it's not small. In fact, at first they thought it's some noise they want to get rid of. Okay, but when they repeatedly cannot get rid of this noise, they realized it has a primordial significance. It was created at the beginning of the universe. So now we can measure this. So if you say there's a temperature, you can measure the different luminosity or intensity at different wavelength or frequency. Okay? So this is the frequency of light or frequency of microwave. And what Hensel-Wilson measure is one point here. But in order to show the temperature, you have to measure the whole curve. Okay? And the green line is what theoretical prediction tells you it should be. Once you know one data point, the whole line is fixed by something called black-body spectrum. And people go ahead and measure at different wavelengths, and you can see the data points are the crosses, and they fit this curve spectacularly well. In fact, I should point out that usually you take data, there's some uncertainty error bars. Okay? So that tells you how big the uncertainties are. So this is a great fit, but actually it's much, much better than this. The error bars actually are much smaller than this curve indicates. We blow up, in this curve, we blow up the errors by 400 times. If I don't blow up the errors, then all the data points will fall right inside this very thin green curve. So it's a spectacular success. And we know the temperature, which is 2.725 degrees Kelvin, which is much better than we can measure temperature in this room. Okay. And this is Beta and people's work. And also, by doing this kind of work, by now we know the age of the universe is 13.7 billion years old. Now, you may not think that's very impressive, but I can assure you that if I go to see a doctor now and ask, can you tell my age to an accuracy of 1%, the doctor cannot do that. So to be able to measure the age of our universe to better than 1%, that's very, very, very non-trivial and impressive. Now, we say that our universe expands. So what does it mean? It means that if you have take 2 points, any 2 points in space, and the distance between them is growing. That is, space is being created between any 2 points. On this Earth, because of all the other forces, we are tied together, so the distance between you and me will not change. We don't move. Okay? But in outer space, the distance between you and me are growing all the time. So this is a lot of so-called real estate being created in outer space. Okay? And this is one of the consequences when we say the universe is expanding. That means space is continuously being created. So this is the simple Big Bang picture. This is today, and we have a pretty good idea of what happened as we go back in time. This is 1 second, and we have very good evidence from a number of different sources that what happened from 1 second on. Now we want to say what happened earlier. Okay? Say a millionth of a second, or even a trillionth of a second, and so on. That will allow us to probe the origin of the universe. So we want to discuss a little bit further back, instead of this part, which is very well understood. Before I go to talk about the early universe, I want to talk about today's universe. Okay? So the question is, what is in our universe today? We all know we are here. We all have atoms, molecules, we have stars. So they probably made of molecules, atoms, and photons. So we know that there's a lot of stuff which is what we see. So all the stars, galaxies are there. And they are all made of atoms, molecules, photons, electrons, and maybe neutrinos. The question is that all? Well, surprisingly, that's not all. All the matter I talk about, atom molecules, and we measure, whatever we know, is ordinary matter. And turn out the ordinary matter contributes only 15% of all the matter in our universe. That means everything we can see contributes only 50%. There's another 85% others. We don't know what they are. Okay? So we don't know what they are, we give them a name. We call it dark matter. And many physicists now today is trying to find out what is this dark matter. So that's not the end of the story. The content in our universe actually has one more component called dark energy. So we have ordinary matter, dark matter, and dark energy. And the ordinary matter that make up us, stars, galaxies, contribute only 4% to the content of the universe. 23% is dark matter, a lot more than us. And then there's something which is even bigger, called dark energy. Why do we call dark energy? Because it's some sort of energy there. And remember, Einstein say energy, matter are both related. And so here we have dark energy, we don't know what it is. Dark matter, we don't know what it is. And then 4%, we do know what they are. So that's very mysterious to us because we thought we were very important. And lo and behold, we find we are only a planet in the solar system. And then we find our solar system is tiny in our galaxy. And now we find not only our galaxy is not important galaxy in our universe, we find that what we are made of, that all these galaxies stars made of contribute only 4% to the content in our universe. Now, we don't know what a matter is, we call dark matter. We don't know dark energies, we call dark energy. So the question is, if they're dark, what's the difference between dark energy and dark matter? This is obvious. If we don't know what they are, how do we know they're two different kind of things? One is energy, one is matter. Well, there's a very simple reason. Consider dark energy to be the blueness of what's in a box. The bluer it is, the more dark energy. So just a way to see what's going on. And let's say dark matter. I have these little star flakes and dark matter. You can think about these as 3 atoms, or you can think about these as 3 stars, or you can think about it as 3 galaxies. Doesn't matter. It's just 3 matter. Okay, that's sitting there. Now, if this region expands, as we say the universe expands, then what happens is that the separation between these 3 will be quite far. So these are dark matter. By dark matter, we mean that the density now is decreasing. So if I have 3 counting of dark matter in a larger volume, then the density will be lower, right? Because the total dark matter is conserved. Matter is conserved. Right? We learned that in elementary physics. Dark energy, that's where it's different, mysterious. The blueness don't change. So that is the dark energy density stay the same as the universe expands. Okay? So dark energy is very different from dark matter. That's why we know there are 2 different dark type of stuff in our universe. So the blueness corresponding to the dark energy density in our universe. So as the universe expands, we can start out, say, yellow is ordinary matter, red is dark matter, and the little blue is the dark energy. Okay? This is the past. Now, as the universe expands, the matter density goes down. Okay? But the dark energy density don't go down. So the content of the dark energy keep increasing as function time. Today we are here. In the future, dark energy is going to dominate. Okay? In the future, as our universe continues to expand, at a certain point, the space will be filled with nothing but dark energy. Because the dark energy density do not decrease as the universe expands, in contrast to ordinary matter or dark matter. That's why we know there are 2 different types of dark stuff. Now, when the universe is very hot, it is simply a gas. Whatever you have, you heat it up, then you will melt liquid. You heat it up to form steam or gas. So when things are very hot, typically will be some gas. Okay? So what is this hot soup or gas like? Well, we can try to study it by looking at the remnants of the hot soup, which we discussed earlier. The remnants of the hot soup is this low temperature, okay? Which is what we talk about this black body spectrum. There's another way to study the hot soup of the early universe, what it's like. And that is go to lab to hit things together. When you hit things together, they create some environment which is very similar to hot. Okay? So that's another way to see when you hit things together, what happens, what comes out. And that is one thing that people are doing. Recreating the early moments of the universe. Much less than a second. They try to reproduce what happened, what it looks like. And this is the machine they are using. You probably have heard of. It's called the LHC. Okay? CERN LHC. This is sitting between Switzerland and France. This is Geneva. You can see the Geneva airport. Okay? This is the airport in Geneva. And this is the ring, 27 kilometers ring, You don't see in the sky because it's 100 meters underground. And what they do is they have protons going very, very high energy and they collide them and see what happens. This is a way to recreate the very early moments of the universe. Many, many countries are participating in these experiments. And you can see that the tunnel, in this, the tunnel is going around, and it's highly bent because this is 27 kilometers tunnel, 100 meters underground. And then they do collide. They will use detector to measure it. This is one of the detectors. There are two, Atlas and CMS. And you can see how big the detector is by looking at these people standing there, these scientists standing there. So this is really, really giant experiments that they are taking data, they're colliding right now, and see what happened right now. And you heard about some results, and you'll hear more this year. They have been getting ready to do this for more than 10 years. And so finally, they are trying to reproduce, recreate the early moments of the universe. This is one way. And they want to find out, maybe this machine can produce some dark matter and they can study them. And if that's the case, then we'll be finding out in a year or two what dark matter is made of, if we are lucky. I should point out another thing. This CERN lab is very expensive and involves many countries into it. And so what happened is that how do you communicate with your collaborators? We are in one group, hundreds of people, hundreds of scientists spread out many countries, thousands of scientists spread out many countries. And the way they decided to communicate is set up something online. And in 1991, CERN set up an online way for the scientists to communicate around the world. And once they set it up, they say, wait, this other people can use too. So they make it free for the public to use it. And this is what we call the web, the WWW, World Wide Web. And it's a product of particle physics research because they're the cutting edge and the communication has been cutting edge. And as a result, and they make it free, which is very important. And from the time they open up, made it free available, within a few years, WWW caught on and have essentially changed our way of communication with each other. These kind of byproducts of scientific research, which is spin-off, can help the community of civilization happen a number of times. You don't know where it will come sometimes, but sometimes it will come in a very big way. In this case, we cannot even put a price tag. How big is WWW online mean to our society today? I don't know how to put a price tag on it. By comparison now, a few $1 billion for the research in CERN is a small price to pay. So now let me go back to what started the hot Big Bang. Okay, because we know the hot Big Bang happened, it was very hot, and then cooling off. So now we say, that's a big explosion. If you have a big explosion, you always want to know what causes the explosion. What exploded? Okay? And to answer that question is what we call the inflationary universe. It's very likely to be the right answer. And so the universe started with a large dark energy density. We mentioned dark energy density, right? So universe started with a very large dark energy density. As the universe expands very rapidly, we call inflate, the dark energy density stays constant. But the space is increasing rapidly. In fact, during that time, the space between 2 points is growing so fast that if I send a light beam towards you during that time, the photon will not reach you because even the photon moves very, very fast. The space being created between you and me are being created much, much faster. So we're going away from each other much faster, and that's how space is created. Very small time, huge amount of space created. Dark energy density stay constant. So all of a sudden, it seems the energy content of the universe have grown a lot. Because remember, energy is energy density times volume. The density stays constant, the volume grows rapidly. Well, at the end, those dark energy can be converted to radiation matter, like atoms or molecules, and that's how we get all the matter in our universe. And leaving behind a very small dark energy today. But that very small dark energy today still contributes 73% roughly of the content in our universe.